everyone! This video is the final requirement for the course ES211 or Statics of Rigid Bodies with Professor Bernadette Dapun. I am going to give 5 examples about center of gravity or centroid, parallel axis theorem, product of inertia, composite area, and mass moment of inertia. So the first topic that will be discussed is the center of gravity or centroid. Centroid consists a location. Centroid is applicable for plane figures having an area, and the location of a centroid can be found using a single integration. So an example of it is locate the center of gravity of the volume and the material is homogeneous. So this is the figure of the problem, and this is the free body diagram. So this formula was based on the area of a circle. So the area of the circle is pi r squared, right? Instead of r, we change it into z to get the dv. So we substitute the value of z here. Z is equal to 1 over 100 y squared, and then just have to square it. So the value of dv is equal to pi over 10,000 y to the 4th dy. So the y with the curved line at the top it represents the coordinates of the center of gravity of each composite part of the body. So y bar is equal to integral of y dv over the integral of the volume dv is equal to the integral of 10 inches to 20 inches of y times pi over 10,000 y to the 4th dy, which is the dv, over the integral of 10 to 20 inches pi over 10,000 y to the 4th dy. So y bar is equal to pi over 60,000 y raised to 6, 20 inches to 10 inches over pi over 50,000. So if you know how to integrate already, y squared over 2, so the y here becomes y to the 6, and then the 2 goes in the denominator, so 10,000 divided by 2 is 50,000. So the centroid is 16.94 inches. So basically, the centroid is at 16 over here. The centroid is 16.9 inches. So let's now proceed to the next topic, which is parallel axis theorem. Parallel axis theorem is used to find the moment of inertia of area about any axis that is parallel to an axis passing through a centroid. So the example is, determine the moment of inertia for the beam's cross-sectional area about the y-axis. So this is the figure that we are going to base in the FPD here. So based on a free body diagram, using the parallel axis theorem, moment of inertia at y-axis is equal to iy prime plus area times dx squared. So the distance here is, this is the length from the center of a segment to the y-axis. So in segment 1, it is 0.5. In segment 2, it is 4 inches. And in segment 3, the center from y-axis is 7.5. We get the iy prime by this formula, which is 1 over 12 times base times the cube of height. So the base of segment 1 is 4 and the height is 1. So we just substitute the value of it, and then the one here, the 96 and 225, came from the square of 0.5 or the center of the segment from the y-axis and multiplied to the area. So we got 1. And then the moment of inertia in y-axis, we use the formula I of y equals to I of y prime plus a dx squared. So we just add this both, and then we got 1.33, 114, and then 225.33. Therefore, the moment of inertia at y-axis is the summation of moment of inertia phi, which is equal to 341 inches to the fourth. So the next topic that we will going to discuss is the product of inertia. Product of inertia is required in order to determine the maximum and minimum moments of inertia for the area. The problem is determine the moments and product of inertia for the shaded area with respect to the u and v axis. So this is the free body diagram with an angle 60 degrees. So first is we get the moment and product of inertia about x and y axis. Since the x-axis is an axis of symmetry, inertia of x and y is equal to 0. So I of x, in the parallel axis theorem, we use the 1 over 12 times base times the cube of height. So here, the moment of inertia along x-axis, we add the two segments. So the first segment, which is C1, 1 over 12 times 20, which is the thickness of the beam, times the height, it is 120 millimeter, and then you cube the height, plus the segment 2, which is the C2. So 1 over 12 times 120, you based it on the second segment, 120 times the cube of the height, which is this, so 20 cube. So if you calculate it, the answer is 2.96 times 10 raised to 6 millimeter to the fourth. So using the parallel axis theorem, which is in the formula of I of y is equal to 1 over 12 base times height cubed plus the area times the squared of the center of the segment from the y-axis. So we just input the data. So we based it on segment 2, which is the 120 times the cube of 20 plus 1 over 12 times 20 in the segment 1 times the cube of 120 plus 20 times the height and the squared of the center of the segment 2 from the y. It is 70, so 70 squared. So the answer is 14.72 times 10 raised to 6 millimeter to the fourth. Next is we get the moment and product of inertia about the inclined u and v axis, which the theta is 60 degrees. So the formula in getting the moment and product of inertia in the inclined axis is I of u is equal to I of x plus I of y over 2 plus I of x minus I of y over 2 times the cosine 2 theta minus inertia of xy sine 2. So we just have to substitute the calculated data we have. So the inertia of x is 2.96 times 10 raised to 6 millimeter to the fourth plus 14.72, which is the inertia at y-axis, and then the value of theta is 60 degrees. So 60 times 2 equals 120. 0 sine 120 is basically 0. So we multiply 10 raised to 6 and then 14.72 times 10 raised to 6. So the answer is 11.78 times 10 raised to 6 millimeter to the fourth, or 11.8 times 10 raised to 6 millimeter to the fourth, so that it will have three significant figures. So the same process in getting the moment and product of inertia about the inclined u and v axis. So we're getting the v axis here. They just have the same formula, but the difference is that it is only sine theta and the other one is sine 2 theta, right? just have to input the data that were solved a while ago. So the inertia at v-axis is 5.90 times 10 raised to 6 millimeter to the fourth. So if we're going to combine both axes, inertia of uv is equal to I of x minus I of y over 2 times sine 2 theta plus I of xy cosine 2 theta. Again, we just have to input the given data which came from the x-axis and the y-axis over 2 times sine 120 because the theta is 60. So 60 times 2, 120 plus 0 cosine 120. So the product of inertia of uv is equal to negative 5.0922 times 10 raised to 6 millimeter to the fourth, which is equal to negative 5.09 times 10 raised to 6 millimeter to the fourth to have a 3 significant value. So the next topic that we will going to discuss is the composite area or the composite body. The composite body consists of a series of connected simpler shaped bodies, and such a body can often be sectioned or divided into its composite parts provided the weight and location of the center of gravity. So the example is the assembly is made from a steel hemisphere. PST is equal to 6.70 milligram per cubic meter, and an aluminum cylinder P of aluminum is equal to 2.60 milligrams per cubic meter. Determine the mass center of the assembly if the height of the cylinder is h is equal to 180 millimeter. So this is the figure, and then the free body diagram. So summation of z bar m is equal to 0.160. So the 0.160 here came from the given 160 millimeter minus 38 times 2/3 pi times 0.160 times the P steel, which is 6.70, plus 0.160 plus the height of the cylinder, which is 180 millimeter, 0.18 over 2 times pi times the height 0.18 times 0.08 here squared times the P aluminum, which is 2.70. So the summation of Z bar M is 6.52529 times 10 raised to negative 3 milligrams times meter. And the summation of the mass is equal to 2/3 pi times 0.160 cube times the P steel 6.70 plus pi times the height 0.18 times the radius, which is 0.08 squared, times the P aluminum, which is 2.70. The summation of M is equal to 67.24851 times 10 raised to negative 3 milligrams. So to get the mass center of the cylinder, summation of Z bar M over summation of M is equal to 6.52529 times 10 raised to negative 3 over 67.24851 times 10 raised to negative 3. So the center mass is equal to 0.097 meter or 97.0 millimeter. So the last topic that we are going to discuss is the mass moment of inertia. The mass moment of inertia of a body is a measure of the body's resistance to angular acceleration. It is used to study rotational motions. So the problem is, determine the mass moment of inertia, Iz, of the frustum of the cone which has a conical depression. The material has a density of 220 kilograms per cubic meter. So this is the figure. The free body diagram is this. The first free body diagram is the figure of the whole cone. The second free body diagram is this little part here. And the third free body diagram is the cone which is inside of the frustum. So from similar triangle, z over 0.2, which is the value of here, is equal to z plus 1 over 0.8. In order to get the z, we just have to transpose the value of h. So 0.8 times z is 0.8z, and 0.2 times z plus 1 equals 0.2 z plus 0.2. So just transpose it to the left, then divide it. So z is equal to 0.33. So the mass moment of inertia of each cone can be determined using this formula. Inertia along z-axis is equal to 3 over 10 mass times the radius squared. So inertia along z-axis is equal to the summation of inertia along z-axis of an element, equals to 3 over 10 times pi over 3 times the radius of the big cone times 1.33, which is the z plus 1. So the z is 0.333 times the density, which is 220, times the radius squared, minus 3 over 10 times pi over 3 times 0.2 squared, which is in the second free body diagram, times 0.33 because the z is 0.333, and then times the density multiplied by the square of the radius, which is the 0.2 meters. We input again the formula, 3 over 10 times pi over 3 times the square of the radius times 0.6, the length of the cone inside the frustum, times the density times the square of the radius. So the mass moment of inertia along z-axis is equal to 37.63 or 37.6 kilogram times meter squared. That ends our discussion. Thank you for watching.